Hi, I'm Mike Wimmer.
I'm Sakin Patel.
I'm Aditya Bhatia.
I'm Nitin Vigasna, and we're Team Alpha One.
So the issue that we're trying to address is often we have problems and challenges, and the solutions that we create don't generalize very well. So, for example, we have instances of wall following here, where the car has to follow a wall to get to a destination, and we have sometimes organic-looking walls and artificial-looking walls, and we have narrower and wider paths. And when we create a solution to get through these, sometimes it doesn't go very well and work very well with other things. So, how can we more effectively create a solution that generalizes well?
So, how do we solve this problem? We can use artificial intelligence. We can use one of the wall following tracks and manually drive the race car in order to collect images where the race car should move forward, left, or right. In order to perform image classification, we use LiDAR images. LiDAR is capable of detecting objects completely around the race car, whereas the color and depth camera are only capable of seeing in front of the race car. This gives the race car more contextual information of its surroundings. Using these images, we can train a model to be able to make decisions on which direction it should move based on the features it perceives.
Humans can easily distinguish the differences between this sports car on the left and this sedan on the right. But how does a computer do the same thing? It uses artificial intelligence image classification to evaluate and identify unique features specific to each vehicle. For example, if an image classification algorithm was made for the sports car versus sedan problem set, it looks at features such as the sports car is much brighter than a sedan, or the sedan takes up more pixels, etc. The main question is, how do we use this to navigate the race car? Image classification is used for the race car to analyze the LiDAR data to help the car to make decisions. For example, this classifier could identify these LiDAR scans as commands for forward, left, and right. We were able to develop and use this to navigate the car through multiple different courses without changes in model code. The classifier can generalize to work in different situations it has never seen before, allowing the vehicle to navigate any wall track without requiring additional training of the model.
Behind the scenes, our image classifier works using a convolutional neural network. A neural network is a computing system that basically functions by using layers of neurons, which are modeled after the neurons in our brain. The beginning neurons are the input layer, which is the labeled images we're passing through. Then you have multiple hidden layers that perform the computations and recognize the patterns, followed by the output layer. The neural network uses weights, which are contained within the hidden layers and transform the input data, controlling how one neuron affects the others. The overall function of a neural network is basically to recognize patterns in the data that is inputted and classify those into a form that is usable for your purpose. So the more good data you provide the network and the more passes you take through the data, the more accurate your neural network will be. The GIF on this slide shows the overall process of an image classifier using labeled photos of a cat and a dog. As you can see, the photos get fed through a filter-like system, which is then used to determine whether they are currently seeing a cat or a dog based on what it has learned through the neural network.
So when it came to actually creating our neural network, we used the Python programming language and the TensorFlow open source library, which is a set of tools to assist in creating neural networks. And we collected our data actually from ourselves driving through the wall following lab. And at each frame, we took an image and classified it or labeled it as being left, right, or forward based on what we were doing at the time. So we used all the data, almost 12,500 images in total, to create the neural network, and TensorFlow helped us adjust each weight after each training pass. And after 10 epochs, or 10 passes through the data of training, we were up to a 95% accuracy of the algorithm estimating whether it's right, left, or forward based on an image. Now we have to test on real courses.
Finally, we ran the model and the results were exceptional. The model was able to generalize to multiple tracks that contain different features.